Good morning, everybody, or good afternoon, as the case may be. Thank you for joining us for this now 12th in the series of the Everything You Need to Know webinars. And this one is everything you need to know about cross-validation. And I'm Barry Wise of Eigenvector Research. And our master of ceremonies today is Bob Roginski.
Hi, this is Bob Roginski, and welcome, and thanks for taking time in your day for joining us. Just a few brief instructions. You probably noticed already that when you join the meeting that you have been automatically muted. Please keep the mute on. What we're doing is we will be addressing questions through the chat function on WebEx. So any questions that you have, just fire away on the chat, and some of them will be answered strictly within the chat by one or more of us from Eigenvector. Some will be brought to Barry's attention to address to everybody. And let's see, we won't be using any video. Barry's just going to be sharing his screen. We suggest that you turn off the video sharing on your own connection, and that's just going to help greatly with the bandwidth. I think that covers it. So
I think that's it, Bob. Thank you very much.
okay.
Okay, so cross-validation. Here's where we're going to go with this morning. I'll talk a little bit about the basics of cross-validation, ways to split data sets up, and then things to consider when choosing your cross-validation method. And then I'm going to talk a bit about how to set up custom cross-validation. I'll say a brief word about cross-validation in PCA, and then how to make cross-validation go bad, and finish with just a bit on variations and related methods. And so I figure we should finish here about Friday afternoon, about 2 o'clock. Okay. That it just, oh, I could literally talk forever about this, I think. And it seems like it's such a simple thing, and yet there is so much to it when you really start thinking about it. So anyhow, let's start with cross-validation, the basic idea. Uh, Cross-validation is done in order to assess how well a model will generalize to independent data, that is, data that is not used in the model development. It has a couple of other names. Sometimes it's known as out-of-sample testing or rotation estimation. And, um, oops. It's most commonly used on predictive models for calibration or classification. And those calibration models, though, can be PLS models, they can be neural network models, they can be support vector machine models, you name it. The same for classification. It can be used in PLSDA, support vector machines, etc. And I want to and it can be adapted for use on descriptive models such as PCA and Parafact. So again, the basic idea continued is what we're going to do is repeatedly split the data into training, that is calibration sets, and test sets or validation sets, and then report results on the test set. And of course, those results are for whatever kind of model that you're making. Often that's a regression type model where you're trying to predict continuous values of an analyte or property, or it could be a classification where you're going to report what class samples belong in. But to continue here, the basic idea is that in each round, samples are in the test set once and only once. There can be multiple rounds with different data splits. And it's often used to optimize metaparameters, and that is, for instance, the number of latent variables that you use in a model, or it could be used to optimize the number of hidden nodes that you have in a neural network. or some of these parameters like the cost function in a support vector machine. It's used to often optimize any number of these other metaparameters to try to improve prediction error or model fitness. So how do we do cross-validation? The general idea is that we're going to take our data set and divide it into J subsets. And then for each one of those subsets, we'll build a model using the samples in the remaining subsets. So let's say we divide our data set into J equals 5 parts. What we'll do is build a model using 4 out of 5 of those parts and apply that model to the last one. Calculate the prediction error for that subset of samples. And if it's a model that's predicting continuous values, then that's just this here, which is that we're just looking at the difference, for instance, between our predicted values of Y, what we're trying to predict, and what the model predicts. And this would be the expression that you have here for a simple regression equation. And then you look at these sum of squared errors right here. But of course, this could be another criteria as well, such as a classification error could go in right there. The important point is that you calculate the prediction error for the subset of samples that you've left out. You look for some minimum in that or knee, like where the point at which it doesn't get any really better. And you add those all up, basically. So you add them up, and the most common way to report that in continuous regression models is the root mean square error of cross-validation. So that's just the sum of all of the errors divided by squared errors divided by the number of samples and then the square root of that. So that's the real common one is RMS ECV in regression models. And if it's a classification model, of course, then it would be a classification error rate, for instance. So graphically, what does it look like? I always like to show this as a picture. I'm kind of graphical myself. So the general idea here in cross-validation is that we've got a data set. We've got X data, which are predictor variables, and Y data, which is a property we're trying to predict. That we take this data set and break it into some number of parts. Here I'm showing it broken into 3 parts. And then what we do is in round 1 here, we would use the first 2 parts to build a model and then use the last X data to predict the last Y using the model that you developed from this. And you would continue, you would then build your model based on this X and this Y, this subset, and then use that model and this X data to predict that Y, and so on. And just repeat that until every section has been left out once. So an example cross-validation curve here looks like this. This is for a model we'll actually use a little later this morning. This is example cross-validation error curve. What we're plotting is the root mean square error of cross-validation for, in this case, the concentration of heptane in a model, and the error of calibration for the concentration of heptane in a model. So generally, cross-validation curves look like this. This is as a function of number of latent variables in a PLS model, but it could be in other models a parameter that typically has to do with model complexity. So you could imagine, for instance, if you're cross-validating in neural networks, you might then cross-validate against number of nodes in the hidden layer here instead of against latent variable number. But if this is a PLS model, it's going to be how many latent variables are in the model. Typically, we get some sort of behavior like this, where the cross-validation error goes down as model complexity goes up, and eventually it either flattens out or sometimes even comes back up again as the model does not generalize well when you have too complex of a model. Here I'm not only showing the error of cross-validation, but the error of calibration. And the error of calibration is generally a little bit lower than the error of cross-validation. And if you've really set things up in any kind of normal way, you're going to always get this kind of behavior where your error of calibration is always somewhat better than your error of cross-validation, because that's a fit to the data where you've used all the data. So again, RMSECV equals root mean square error. I should have put the word square there, of cross-validation. And it's the estimate of prediction error on independent data. And RMSEC is the root mean square error of calibration, and that's on the fit to all the data. So the problem is, at least the first one, how do you split up the data? There's a lot of ways to do that. Well, first thing you might want to think about is, how should a model be tested? If you're going to test a model, how do you want to do that? Well, tests should be tough but fair. And our colleague Don Dahlberg likes to use this example. He's a professor at Lebanon Valley College in Pennsylvania. And he talks about making up tests for students. Well, how should you do that? Well, first off, the questions that you put on a test shouldn't be identical to ones they've already had before, because then they could just remember the ones they've already worked for and through and write down the answer. So you don't want them to be identical, but they should be similar. It should be in the same domain of information that you've been working in. So when you do cross-validation, the really thing to think about is how to split up your data set in a way such that test samples are not identical to training samples, and test samples, though, should be similar to training samples. So you shouldn't have test samples that are far removed from the data that you're modeling on, because we generally don't expect our models to be able to extrapolate far away from the data anyhow. But beyond that, how do you do splits? How many subsets do you split things in? How to do the splits? I had some fun with this today. Yesterday, I got to thinking, how many ways are there to split 30 samples into 6 groups? Well, there's about 1.8 times 10 to the 19 is what I got for that. So there's a lot of different ways to do splits of data. And here are the common ones. So the formation of the test sets. The first one, this is for dividing a data set into 3, but you can generalize this to dividing into way more sets if you like. We call this Venetian blinds. I think sometimes they call it K-fold. We've called it Venetian blinds just because that's what it looks like when you draw it. But in this case, here are your subsets, or the parts that are all the same color, and you see that, for instance, the red one here is the 3rd, 6th, 9, 12th sample, and that forms one of the test sets. Another way to do this is to use contiguous blocks, and that is actually best for time series data. So if you have data from a process where you could have autocorrelated noise, and that means, for instance, process disturbances that happen that take time to decay, then you typically want to divide your data set into contiguous blocks because otherwise your noise on adjacent samples, your errors is correlated. And if you use take one sample out of the middle of the other two, then the noise on the ones on either side is correlated with the noise on that one. And that tends to tell you to keep too many factors in your model. However, the noise in this block here is probably not correlated to the noise in that block there. And that's why you want to make sure that you split it in a way so that your noise in your test samples is not correlated with the noise in the calibration samples. So you can also do random selection, usually repeated a number of times. And of course, if you have small data sets, you can use leave one out, where each sample forms a test set by itself. So what else can you do here? You can do custom selection based on prior knowledge. And we're going to talk a little bit about how to set that up as well. But before that, I'm going to go back to an old example that we've used again and again, and use this to show some cross-validation. So here is our old slurry-fed ceramic melter. This is a process that I worked with long, long ago at Pacific Northwest National Labs. And in this process, you're going to take nuclear waste, mix it with glass-forming chemicals, and melt it into a glass that's a solid waste product. And so the data here is that there are 20 locations of temperatures, and this is what those temperatures look like versus time is right here. And the level of this system goes up and down as glass is poured in and off of it. So what we want to do is build a backup to the pneumatic level detector and see if we can build a model that relates the temperatures in here to the level. And we expect that there should be a relationship, because as the molten glass level in here changes, that changes the temperature profile on these thermocouple locations. So the data looks like this. We've got our 20 temperatures marching along here in time. You see the sawtooth pattern in the data. Well, that sawtooth pattern is related to the level of the glass is going up and down. The glass tank fills up, and then it's dropped pretty quickly as it's poured off into a canister, and it goes up again, and that's how it works. So our data is 30 by 20 temperatures, and our Y block is that 300 by 20 temperatures, 300 samples, and the Y block is 300 by 1, and that's the glass level. Okay, so this is an oldie but a goodie here. I'm going to go to my MATLAB now, and let me see. Wow. Okay. I haven't even started my browse window yet. So if you're using PLS Toolbox under MATLAB, then when you type browse at the command window, it should bring up the PLS workspace browser. And of course, if you're using Solo, this is the interface that you start from. I'm not going to use these other MATLAB windows now, so I'm going to dismiss them and just park them. And I'm going to work from the workspace browser. And I think I'll also actually minimize my PowerPoint here. So I'm going to bring some data into the workspace here. So I've got my data folder, and I've got my slurry-fed ceramic melter data. And I've actually already excluded some outliers in this data set. And so I've got this set up, and I'm going to now start up the PLS interface. That's one of my favorites here. So I think most of the people on this call are already users, so you're probably fairly familiar with what our software looks like. this is the main window that you start from when you want to use the interfaces in our software, which most people do, and which I do most of the time nowadays. Uh, these are the tools here. Here are the data that we're working with, and here's our model cache down here. But I'm going to start at PLS. And there's our interface. And I'm going to load my data in, my X and my Y. And I want for an X, the X block with the outliers excluded. And for the Y block, which is that level. I'm going to set my pre-processing to be mean center, because I know that works in this data set already. But now let's go ahead and look at the cross-validation window. So to get to the cross-validation window, I hit this little check mark here, and the cross-validation window pops up. And give that a second to draw itself. Okay, this is going to be how it goes this morning. So we have our set. Bob, have you ever seen this one before? My colors aren't drawing here.
Huh.
And it was working today. Okay, well I will persevere here. So we have a number of cross-validation methods here to work with. We could do, of course, none. We can turn cross-validation off here, and we could do random subsets. We can do contiguous blocks. We can do Venetian blinds. We can do leave one out, and we can do none. And I'm going to guess that this has to do with the fact that we've been fussing with this interface a little bit, but normally up here in the top, you see a graphic that shows you how your data set is split up. And so I'm going to be without the graphic today. And I'm going to, though, first show you what would happen if we do the right thing here and do contiguous blocks. So I'm going to set this to just 12 latent variables. I know I'm not going to need any more than that. This data set's large, so I'm going to split this into 10 parts. And I'm going to say, okay. And then I'm going to go ahead and get a model. And this chooses 3 latent variables in this model. But what I want to look at is my cross-validation curves. And this is what I get for my root mean square error cross-validation here and my error calibration in this data set when I've done this the right way. And you'll note here, this looks like 3 factors in this model is pretty good idea. I'm going to, let's just look at only the error cross-validation curve. Things get a little better on the 4th one, but not much, and we're going to talk about that. After that, the prediction error gets worse. And so 3 factors was a pretty good choice for this model, a very good choice. And also for my variance captured table, that supports that because my variance captured in Y gets really small after that 3rd factor. So I'm going to do this. I'm going to say spawn a static view of this right here. And now I'm going to go back to my cross-validation window, and I'm going to change this to Venetian blinds. and say, okay, and run this again. And interestingly, the automatic model selection actually wanted to choose 4 for this. And you see now that the curve looks a bit different. Now, when you do Venetian blinds on this and split this up in a way that I wouldn't, you actually see that it looks like maybe having that 4th factor in here is good. And in fact, the model doesn't turn around and start getting worse until after 6. And that is really because I'm drawing samples out that are surrounded by other samples in a time series. And that then tells the model that fitting it harder should work. Well, in reality, it won't, because that's not the way we do predictions. We do predictions at future times that are unrelated to now. So in fact, this is the one that makes more sense. And if you actually look at this, you'll notice that the scales here are a bit different. This has an error of 0.105 here, and this is up at 0.11. So these are actually on this one here is quite a bit higher than that. And this is really the more realistic one, the one where we've divided our data set up using block cross-validation. Okay, I'm going to go back to PowerPoint and get going again on that. So there's a lot of things to think about when doing cross-validation. First off, how are you going to, well, first off, how many objects do you have? How many samples do you have? In what order are they in the data set? So I just showed an example here from the Melter data where order was important because it was a time series. But it can be important for other reasons when data was collected also. And you may find effects in data, for instance, like the fact that your laboratory heats up over the day that causes changes in the instruments to have drift over time. You also want to think about what's the objective of your cross-validation. Are you trying to minimize a specific type of error or an error only within a certain range of your data? You also want to think about the presence or absence of replicates, and we're going to talk about replicates here a little more. And
Barry, if I can interject for just a moment, and so you're going to be getting to the topic of replicates, but we've already had a question, and I'm going to read it to you. In case of replicate measurements, how is the best way to configure the formation of test sets for cross-validation? Should I use the average of the replicate measurements? Neil replied, "Are they true replicates or just repeat measurements?" And the submitter, Eduardo, said an answer for both cases would be great. So just wanted to set that up for you. And when you get to the topic, if you can address Eduardo's question, that'd be great.
I will. I will. I'm going to hold off on that for just a minute.
All right. Thanks, Barry.
Sure. And that's this, the traps to avoid. The replicate sample trap. Okay. Let's first define what a true replicate is. A true replicate is samples that are supposed to be the same, but have all the same, but have an opportunity to have all the sources of error be different that are normally associated with how things our samples are made. What do I mean by that? Okay, let's first think about a repeat measurement. A repeat measurement is where you take the same sample and you just put it in the machine again and you press the button. Okay, that sample, the errors in the makeup of that sample in terms of if you had messed up solutions or you didn't do your pipetting exactly correctly, all of those errors in that sample are the same both times you measure it. The only difference is the instrument noise when you set it in or when you punch the button twice. So a true replicate is a sample that was two samples that were made up from scratch that are trying to be the same but have different errors in them. Okay, so different replicates should be in both the model and the test set. So if they're really true replicates with different sources of error, then you should split them between calibration and test. But if they are actually repeat measurements, they should always be kept together because they have the same sources of error. And what you don't want to do, if you split those up, then fitting the source of error in one fits the other because they're really the same. And you don't want the model to think that it can do that. Okay, I'm anthropomorphizing the model there. But so that's one trap you want to avoid. True replicates, split them up. Repeat measurements, keep them together. Another trap to avoid is the external subset selection trap, and that is the extrapolation. So this is when your test set space is outside of your model set space. So especially if you've done an experimental design, you may have corner points in your design that are really extrapolations from the rest of the data. And that is, if you leave that point out, you have no other data around it. And so if you're trying to predict it from the rest of your data, it's really an extrapolation from the rest of the data. So you want to be careful about setting things up so you don't do that. And then there's outliers, because outliers will screw pretty much everything up. Um, if you leave outliers in your data set, you're really going to get spurious cross-validation results because they tend to have large error values that will swamp everything out, and your overall cross-validation performance will depend heavily on just how well it did on those samples. And so you really want to make sure that you get outliers out of your data sets. And so let's just quickly here, I'm going to go back to my MATLAB and show you what happens. I'm going to take this and I'll spawn this picture off so we can hang on to it. Spawn a static view of it. Okay, so we keep it around. And then I'm going to click on my X and say reset include all rows in my data. There's about 6 data points in here that I got rid of before I did this. And I'm going to go ahead and click the model button now and watch what happens. And oh, I'm going to change my cross val back to contiguous blocks. Let me do that. And now I get a cross-validation curve looks like that, which sort of says that it looks like 2 factors might be a good choice, or it has a minimum of 5, but you'll notice that its character has changed a lot. This is what we had when we had our outliers removed and contiguous block cross-validation like is appropriate in here. And here we see that with the outliers in, we get quite a bit different behavior. Overall, the errors, of course, are a lot higher here. But that's the issue. So here I can actually show you what samples we removed in here. And if I They're pretty easy to find when you include more factors in this model. But the ones that we actually got rid of were these. That one, that one, that one, that one, that one, and that one. Okay. And so when you throw these samples, this is a leverage versus studentized residual plot. When you throw those in, then you really get a much different looking cross-validation plot. Okay. So Chuck Miller used to work for us. He works for Camo now, and Chuck is a very thorough guy, and he created this cross-validation usage matrix and talks about all the ins and outs of doing cross-validation. And across the top is cross-validation methods, Venetian blinds, contiguous blocks, random subsets, leave one out, custom, and then talks about the data set types here. Well, for general, Venetian blinds is easy. It's relatively quick. Contiguous blocks is also easy. Random subsets can be slow if you have a large number of iterations or a large number of samples, and the selection of subsets that you get is unknown if you do it randomly. Leave one out is really easy because there's only one parameter to choose. Avoid using if you have more than 20 samples. So you should really only do leave one out cross-validation for small data sets. Custom cross-validation is great because it's flexible, but it requires time to define the splits. If you do have small data sets, then leave one out is a good choice unless it's designed data, and that is if you have a DOE with corner points that you shouldn't leave out, then you need to think about that. And often you need to do custom in this case to avoid the external subset selection trap. Randomly distributed objects, then Venetian blinds and contiguous will both work fine. Random subsets would be good. It can take a long time. Leave one out, okay, but can take a while with large M, but generally you only want to use that if it's small data sets. And if you didn't think there was enough detail in here yet, there's more. Okay, with time series data, we really want to use contiguous blocks, useful for assessing temporal stability of models. This is also, though, important in other instances where your instrument might drift. It might be that nominally the samples aren't the time series themselves, but the instruments effectively are because of the way they drift over time due to environmental conditions they're in. Let's see what else. Batch data. Venetian blinds useful for assessing predictability within batches, whereas contiguous is useful for assessing predictability between batches. If you have block data with replicates, beware the replicate sample trap. You'll get over optimistic results. Contiguous blocks, it's a good way to avoid the replicate sample trap. One thing, especially leave one out, is going to be overly optimistic due to the replicate sample trap. And then finally here with designed experiments, DOE data, Venetian blinds is dangerous unless the object order is randomized, as is contiguous blocks. Leave one out really isn't recommended, and often you really need to do custom if you've got designed data. Okay. And about custom, we're going to talk about that in a minute, but what you might want to do in designed experimental data is have all of your corner points in your design not be cross-validated over, and instead just cross-validate over the interior points.
Barry, we had a question. When selecting the optimum number of latent variables, do we consider only RMSE CV? Or is it necessary to look at other model statistics such as R squared or slope? Thanks.
Yeah, okay. That's sort of addressed in this slide. First off, the choice isn't always simple. Number of PCs, latent variables, or other parameters. That's like nodes in a neural network or a cost parameter in a support vector machine, etc. So, your choice isn't always simple. A few rules of thumb. Uh, Square root of number of samples is a good choice for number of splits. I'm kind of starting to rethink that, at least as the data sets get small. Um, it's useful to do repeated cross validations with different data ordering. Uh, be conservative. This is perhaps one of the most important rules. Models are more often overfit than underfit. The best choice is often not the global minimum. That was actually supposed to say RMSECV. I missed the C on that, or the V. Look for a minimum and work backwards to a more parsimonious model if the improvement isn't at least 2%. At least that one works in PLS really well. Other methods, I don't know how generally applicable that is, but always be aware that if you only get just slightly better performance and it's at the cost of making the model more complex, is you're always making a slightly more brittle model anytime you let the complexity increase. And so be real wary of small gains in error cross validation that you've gotten at the expense of adding parameters to a model. And look to see if your error calibration is less than your error cross validation by more than about 20%. And that'll indicate overfit. That number is the overfit number. The more data you have, the smaller that percentage of concern would be. The less data you have, the bigger. 20% is kind of for sort of medium-sized data sets. Look at your variance captured in X and Y for PLS type models and ask yourself if it's significant with respect to what you know about the data. But the important thing here is use all the info you have, not just the RMSECV. You may know some other things about data, for instance, like the rank that you expect your data to be based on how it was made up and what analytes are in it. So use everything you know. So Bob, did I answer that question?
I think so. I think so.
Okay.
Maybe just a comment on how we prefer looking, especially for regression models, root mean squared error of cross validation and prediction as opposed to R squared.
Oh yeah, not a fan of R squared, because the problem with R squared is that it's affected by the range. Okay, if you have an error of zero point 0.1 mole on your prediction error for a concentration, your R squared will get better and better as your data goes over a wider range, even though the error stays the same. And what we're usually interested in is minimizing the error because we're going to use that number somewhere else, like in a process control scheme. So really, that's why the RMS ECV stats are much preferred to the R squared. For one thing, RMS ECV is in the same units as the variable you're trying to predict. And that then makes it really pretty useful. So again, I won't get too sidetracked into that, but yeah, we're not generally fans of R squared.
A question from Sophie. In another webinar, the instructor saved another subset for prediction. When do you recommend this step?
Yeah, if you have a final validation set, when you're done, after you've been through all of this. Yep. So I want to talk just a bit about custom cross-validation setup. Samples can be coded to tell the cross-validation interface or the command line how to split them up. And they can be stored as a class set in our dataset objects. And the trick here in doing this is to code them where your test sets are uh, coded as 1, 2, 3, whether the first split, the second split, the third split, etc. Unused samples are coded as zeros. Samples that are always in a calibration set are coded as -1s, and samples that are always in a test set are coded as -2s. So hopefully you folks are familiar with the dataset object. And here's just a picture of it. The data set has a place for everything and everything in its place. And the DSO keeps metadata associated with data sets organized and accessible. Um, and it also includes information often used for visualization, but we can set up classes here to include how we want to cross-validate things. So let me go. So, all right, this is all our stuff normally in a DSO. So for our custom cross-validation example, we're going to use the near-infrared spectra of pseudo-gasoline samples. And it's this data set that's in the toolbox in Solo already as an example data set. So here it is, near-infrared spectra of pseudo-gasolines. There are 30 samples. It's the absorbance at 401 channels from 800 to 1600 nanometers. And there are 5 analytes in this: heptane, isooctane, toluene, xylene, and decane. Okay, so I'm going to go to MATLAB and I'm going to close this.
Hey, Barry,
Hey, Lyle.
I think if you close your analysis window, which I don't know if you were about to do, and reopen, I think your cross-val window should look correct.
Okay. Well, my analysis window
Or
is
cross-val.
so you want me to restart browse?
No,
I
I
will.
just think
I'll close it.
okay.
Okay. See if you're right. I'm hoping you are, because I could use a little bit of that today. So, um, okay. So I just loaded up a data set here, which is our spectra and our concentrations here for this. And so I'm going to start PLS again. And I'm going to load this data up. So Lyle, I hope you're right, because that would really make my day. So my X data is spec 1 with the cross-validation sets. And my Y data is my concentrations. And I'm going to select my Y columns. I just want to model heptane here is all. So I'm going to model heptane. I'm going to set pre-processing in X to be real simple, mean center. And let's actually go, oh, there it is. And so this is what I was hoping to show earlier. And the bar across the top actually shows you graphically how your data sets are split up. And here it's shown as Venetian blinds. This is how my test sets are split, and you can see here with a 10-way split, the data, every 10th bar is the same color. You know, if we this as contiguous blocks, it would show it here that you're blocking it up different. And so that was what I was sort of hoping to show earlier. But what I'm going to close this again here and just say okay. But what I want to show you is the dataset object and how I set this up. So I'm going to click on X and I'm going to say edit data. And here is my dataset editor with my data table, but let's look at the row labels. And so I set up two different classes in here. So this is for my two different class sets. One here is heptane high-low. And what it does is it takes the points that are out on the end, either really low heptane values or high, and it calls them the extremes. And we're going to leave those data points be always in the model. And then the rest of the data is just split into three parts in the center. Let me show you this from the class lookup table. When I say edit class lookup table, and you'll see here how this is coded. So I've got class -1, which is my extreme points, and then 0, there aren't any zeros, and then I've got 3 splits of the data with 6 samples each. So that's okay. I'm going to close this. And so now if I go back to cross-validation, I can choose custom. And when I choose custom, it says define custom cross-val sets. I'm going to say select class set. And I've actually got two in here. I'm going to use this first one, heptane high-low. And I'm going to use that for my class sets. This actually shows you graphically what that looks like. So the ones that are in all the time are the dark are those, and I'm going to say okay. And now when I do cross-validation on this model, what it's actually doing is it's taking extreme points and they're always in. And so it's assessing then how well the model works on just the interior points. And let's go ahead and get that up. And here I'll just bring my regression curve out. So this is the YCV predicted heptane right here. And this is over the range of 12 to 24. So these are my cross-validated predictions, but let's look at the fit of everything. If I look at the Y predicted here, these ones in are points that are the extreme ones that are always in the model. And so when I went to cross-validation, it just looked at these ones here in the middle and to see how well those cross-validated when the outer ones are always in the model. Now, why might you want to do that? Well, it could be that you mostly care about how well your model works on the interior range of the data. You've put extreme samples in the data set in order to have samples that have the best signal to noise to model on. But what you really care about here is perhaps performance in the middle where your process is going to operate. So that's one way, for instance, we could use custom cross-validation here. Okay, I better get moving here because I'm taking plenty of time. So hopefully that showed you how to do this. I will tell you that this feature will be enabled in the next version of PLS Toolbox, which will be, and Solo, which will be out in about a month. You can still choose custom cross-validation sets right now, but you just have to load the numbers out of the workspace. Okay. A few more things to talk about. Well, how do you do cross-validation in PCA? Because in these predictive models, we have a Y variable that's either a value or a class we're trying to predict. What about in PCA? Well, we developed a method for that quite a long time ago, actually, where what we do is we break the data sets up just like we do in normal cross-validation, and then use all but one of those to build a PCA model. And then this is the tricky part. You take the remaining data and you split it up, and you model derived from this part, and this part of the data to estimate variables that you've left out. And that actually works well for estimating how many factors should be in a PCA model. It's not perfect. None of the methods are, but it's usually a pretty good indicator. Okay. And I'm going to skip demonstrating that on the SFCM data with outliers removed in the interest of time. We'll talk briefly about this. How do you make cross-validation go bad? Well, there's all the things that we mentioned. Outliers can make it go bad. Handling replicates inappropriately can make it go bad. Doing inappropriate splits of the data, like using Venetian blinds when you ought to be using block cross-validation, all those sort of things can make it go bad. Using subsets that are too small to affect model stability. One of the things you're really trying to test here is how stable the model is, so that it actually has an effect on the model. And leave one out, cross-validation, just really doesn't do that. You know, anytime you have more than 30 samples or so in a model, when you're doing leave one out cross-validation, it doesn't really change the model anytime you leave just a single sample out. It doesn't adequately test that. Using only one split of the data, it's a good idea to change that up. But a really good way to make it go bad is to give cross-validation too many things to choose from. And that is, if you try too many different things with your data, like hundreds of different pre-processing methods, then you can possibly find something that seems to cross-validate well that really doesn't generalize. This is especially true in variable selection, when you really ought to randomize your cross-validation. But I'll just show you quickly a way of making this go bad. So you can try this one yourself at home. I just created some random data. I said X equals rand 80 samples by 2,000 variables, and Y equals random value 80 by 1. So I'm going to try to build a model to use X to predict Y. And we know that there's no way that you should be able to do that because this is just random, okay? But if you use cross-validation to choose 35 variables for an MLR model, well, you might be surprised what you get. So here, this is just how to set it up in the interface. When you've clicked on variable selection, I loaded this random data in and then used interval PLS in MLR mode and said choose 35 variables using forward stepwise and choose them by cross-validation. And lo and behold, this is what you get. This is a cross-validated prediction right here. And that's what it looks like. It looks like there's something there. All right. But when you try it on a brand new test set, of course, you find out that it's complete garbage. And so, you know, this doesn't work. You can't predict a random Y variable from random X data. That just doesn't work. But if you give yourself enough things to choose from and select them via cross-validation, you can make it go wrong. You can make it look like it. And this is why this is really important in these, you know, big, wide data sets and with lots and lots of variables and not very many samples. When you start selecting variables out of them, oh, you know, this is a problem. It's very difficult problem, which is why it's really important to always have test sets to try things on. I wanted to just mention just a couple of related methods. Nested cross-validation, which is also known as cross-model validation. This can be important at times where what you do is you segment your data set, leaving part of it out, and then you just cross-validate within that subset and choose your metaparameters from within that subset and then test them on the remaining data and repeat that. So you're really nesting the cross-validation. And in small data sets, this can be quite useful. In large ones, it really doesn't make a lot of difference. I know some people that are fans of this, especially Rasmus Bro. So we're working on implementing being able to do this. Okay. Anytime people say bootstrap, that generally means that they're doing resampling of their data set with the replacement. And that means that for calibration and test sets, you pull samples out at random, but then put them back in. So there's the possibility that samples can be in multiple times in calibration or test set and can be not in there at all. And that's bootstrap. Jackknife is similar to leave one out cross-validation, typically used to estimate variance in the parameters. And in fact, from the command line, you can use our cross-val functions to do jackknife and also permutation testing. Permutation testing is where you randomize your property to be predicted or your class membership and see if you can get a model between that and try that many hundreds of times and see how often you actually get a significant model. And if you're getting significant models or that look significant with randomized Y, you know you have a problem. And that's why permutation testing is done. All right. So conclusions. Lots of things to think about with cross-validation. In a nutshell, remove outliers. Okay, outliers cause such big headaches. So you really need to work carefully through your data and establish that to begin with. Remember the tough but fair principle. I think if you do that, then you can't go too far wrong. If you remember that you're always trying to make it so that your left out test sets are tough, but they're fair. You would expect the model to be able to predict them. Test in a way that is relevant to your goals. In the example that I showed with the near infrared data, if you really only care about how well your model performs in a limited range of your data, then it's a good idea to test it on just that limited range and see how it's doing on that. And that might affect how you set your parameters in your model. It may be that you can improve the model in that specific area with a different set of parameters than if you're trying to optimize over the whole range of your data. And that's what you really want to do. You want your models to be fit for purpose. And make sure you validate your final model on separate independent test sets, especially if you've jumped through a lot of hoops, tried a lot of different things, all that bit. You want to make sure you didn't fool yourself by finding something that just happens to work for the sample of the data that you have. And then I hope you're convinced that PLS Toolbox and Solo allow you great flexibility in choosing proper cross-validation. And with that, I'd like to raise a beer to those of you who are in the cocktail hour time zones. And I'd be happy to take some questions. What do you got, Bob?
Okay. When do we use just cross-validation versus having an actual test set? And Rasmus piped in, cross-validation is used when you don't have 1 million samples. If you have loads of data, you could skip cross-validation and just have a test set. Cross-validation gives you more value, so to speak, because all samples are used for calibration as well as for validation. And if there was anything you wanted to add on to that, Barry?
Oh yeah, who would I be to argue with that? No, I think that's great, and that's really true. When you have a million samples, then this is not nearly that important. And in fact, that's typically not our world. It is some people's world. Uh, as chemometricians, we tend to work mostly with people that are um, developing systems. And when you're in the development phase, you usually don't have tons of data. And and these sorts of issues are really important then. Um, so yeah, I'll just second that is all. What else we got?
That is it.
That is it.
Yes.
Okay. Well, thanks everybody for joining us. I really enjoyed putting this together, and we also hope that maybe some of you will join us for our online EigenU, which starts on September 15th. And so this year it's entirely online. We hope someday to go back to in person, but we're not there yet. And so hope to see you there. And thanks very much for coming.